Hi, today we're going to talk about optimization, which is story problems. Yay! Story problems is probably the favorite part of calculus for most students. Okay, no, not really. It's actually one of the least favorite. But hopefully, this video will show you it's not something to dread. It's just something to do. There are some really direct steps that if you follow them, make it a lot easier. Not all of the steps are easy, but it makes it easier. And then we'll do an example and see what happens. So, the steps. Here they are. 1 through 6. First, the first thing to do is you read this problem. It's a story problem. Actually, it's not really a story. Stories have plots, they have character development, resolution. It's just a question written in words. It's like a paragraph. Anyway, but you read it. The goal here is to read it, but more than read it. At this point, you should be able to read this. It doesn't require much. A second grade education could probably do it, and you're in college. So, understand is really the important part. That doesn't mean that you look and go, oh, I can solve that. I know exactly what they're talking about. It means you understand the pieces of it. You can break it down. You can find the little bits in there. You can say, that means something. That means something. That's what they're looking for. That sort of thing. Once you understand that, draw a picture. Not every optimization problem requires a picture. Some are formulas, some are even more direct, and you don't even have to, you can go directly to a formula, you don't have to have a picture, because you have a mental image or you just know what's going on. Most of them, some kind of drawing or something is going to be in there. And label everything. Like an X, like a Y, like a whatever. And there's going to be relationships. I'll just write down here. There's relationships between the variables. The X's and the Y's get together for some kind of relationship. The X's and the Z's, the M's and the G's, whatever it is. There's another piece that separates this from a general story problem, though. These are optimization problems. They're a min or a max. It doesn't always say min max. It might say most or least or largest or some word that kind of implies a min or a max. You need to figure out what's being optimized and write a formula for it. By a formula, I really mean a function of one variable. Ultimately, we draw the pictures, identify, and then relate the variables to get a function of one variable. Why a function of one variable? Well, if it's in only one variable, we can use calculus. We're going to find absolute maximum or minimum here. That was stuff we learned a little while ago. An absolute max or min, we need to test endpoints, we need to find critical points, that sort of thing. Now the endpoints are a little bit tricky sometimes in some of these, and sometimes they don't really exist and we just have to sort of logically go through that, but it works out pretty well. This is not the hardest step. Actually, now the last step seems like it shouldn't be there. We have to answer the question. But usually they're asking for something. How big should I make my pool in order to maximize? Well, what's the answer? The answer is the bigness of the pool, the dimensions or whatever. How many times should I go to the store in order to blah, blah, blah? Well, the answer is the number of times. A lot of times students answer these problems, they go to here, they stop. They have solved what the critical point is, and they don't actually go any farther. And if that's not actually what's being asked, they didn't answer the question. Okay, let's take all these and put it together. I'll read this off. I'll give you a couple seconds, plus pause, you can take as long as you want, to try to figure out using those steps. A farmer has 500 feet of fencing. She wants to enclose a rectangular pen. What dimensions should she use to maximize the area of the pen? Okay, hopefully you have time to think about that. The first thing is to read it and understand. I just read it for you, so hopefully you did get the reading part. The understand, break this down into little bits. Farmer has 500 feet of fencing. There's a little bit. Wants to enclose a rectangular pen. What dimensions to maximize the area of the pen? You don't have to highlight your whole paragraph in different ways if you don't want to. But there are 4 bits here. She has fencing. She wants to enclose a rectangular pen with fencing, and is asking for dimensions to maximize. So that's what's going on. Now the second step is to draw a picture. What am I drawing a picture of? The fence? I could do that. But this is really not going to help us. Because really, that's not the goal. The goal is not what kind of fence, etc. The goal is to draw a picture of what? The interesting thing is this rectangular pen, because we want to know the dimensions of it. So what's a rectangular pen going to look like? Like that. Now that looks like a square. A square is a type of rectangle, but It doesn't really matter. What's key on this, though, is to label everything. If this is a rectangle, what can we label? We know those are all 90-degree angles, so we don't need to worry about that. I need something here to label this, so I'm going to call that x. Hopefully now you can think about this. What do I call this? Is that necessarily the same? It might be the same. Squares are rectangles, but it might be different, so I'm going to call it y. Now I could call this z, but actually we know it's a rectangle. If it's a rectangle, it's got to be x, and this has to be y. Now, that is our picture. We've used the enclosing the rectangular pen information, but we have more information. We have 500 feet of fencing. How does that relate to this? Well, this is fence, 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 fence. So we know x plus y plus x plus y is 500. Well, actually, it could be less than 500. It's less than or equal to. But if we're really going to maximize the area, it stands to reason that you want to use all your fencing if possible. That's not always the case, but pretty much. And let's simplify that a little bit. 2x plus 2y is 500. That's part of our picture. Okay, it's a relationship. It's one of the things that relates our variables. Now, step 3. So this is step 2. Step 3. We need to identify the thing being optimized. What's being maxed or minimized? It's maximized the area. So we need the area function. The area of a rectangle is just x times y. And that's good, but it has 2 variables. So we need to get rid of a variable. We want to have only one variable left. So we need to get rid of the x or the y. We're much more comfortable with x's typically, so I'll get rid of the y. And how do I do it? I use this. Because this tells me, well, let's solve for y and plug it in. Let's see. 2y is going to equal 500 minus 2x, or y is going to equal 250 minus x. And I can plug that in here, so that area is x times 250 minus x. We're done, although I want to simplify that because that's just a little bit easier. I'm going to multiply it through. I get 250x minus x squared. Now, that's step 4. We're almost done. Step 5 is use calculus. Use calculus to maximize this. How do we maximize this? Well, we take its derivative and find the critical points. So I need the derivative. And that should be pretty easy. Critical points are where that 0 or doesn't exist. It's polynomial, so that doesn't exist. The doesn't exist points don't exist. There aren't any. So put the equal 0 does, and we can just solve that, bring that over, divide, and get x is 125. I might need y at the end, but right now I'm still in the process of calculus, so I don't really need the y. But I do need endpoints. So I need to think, for x, this is the critical point. Endpoints. How big could x be? Well, think about this. I have 500 feet of fencing. If I want to make this as big as and that as big as I can, there are 2 x's. Even if I put nothing in y, x can't be more than 250. Likewise, from a very real standpoint, x can't be lower than 0. Those are the endpoints, that's the critical point. In absolute maxes and minimums, what do? You plug them all back into the original a. So a of 0, a of 125, a of 250, a of 0, plug 0 in here, I get 0. A of, I'll skip ahead, 250, plug it in here, you get 0. A of 125, I'm going to get something else. 250 times 125 minus 125 squared is going to be equal to, I'm not sure. Let's find out. In any case, it should be clear, even before I did that, this is the absolute max. Why? Because the other 2 are 0. That's our answer. Oh wait, is that our answer? Remember, it's important in step 6 to actually look at the question and figure out what we wanted. What dimensions? That's what we're looking for. So, we know x has to be 125, and y is the other dimension of our rectangle. How do you find it? Let's look back to see what y is in terms of x. Right here. Y is 250 minus x, so 250 minus 125 is also 125. And these are feet, because that's the units we're using. It turns out the best rectangle for this job is in fact a square. Hopefully, it gives you an idea how to try it. Play around with these. You'll find they're not as bad as you think. Until next time, this is Dr. Jack.